So Julia has upped the ante on the design spec for this facility. Let's move now on to a physics talk from Amelle Zair at King's College London.
Okay, so good morning, everyone, and good morning to the people in the audience, but also online. I'm very glad to be here to present the physics part of this, this XFEL project. And as you can see here, it's all the different sciences that we've been covering, and this is all the people contributing. And in my case, I'm representing the physical sciences, and I've been working with Adam Kerender, Jason Greenwood, and John Maringus on this part of the project. Okay, so the next generation of X-ray free electron laser can enable lots of physical experiments, physics experiments. And basically what we are looking for is really high intense XFEL. So we're looking into intensity in the range of 10 to the 18, 10 to the 22 watt per centimeter square. And we want to get this unique opportunity to go into the very short time scale. So we've been listening to Julia's and Alan's presentation. They were talking about femtosecond scale, but in physics, what matters is to go at the attosecond time scale, because this is where we can scrutinize matter at the quantum level. And of course, we are interested in having high repetition rate to the megahertz level, because the type of physics we are tracking here is very rare event. So high repetition rate is a perfect tool for that. I will just bring you to 3 examples of highlights across physics. There are many, but I would like to focus on those 3, from basically more like physical chemistry to actual control of at the quantum level, and towards really matter under extreme conditions. And then I will show you a bit of new opportunities that this next generation of XFEL offer. So the first part is about X-ray spectroscopy. And what we want to do is to understand energy transfer. So a good example of that is the investigation that has been done in DNA to understand basically damage. But what is really important here is to understand that what we want to do is to take snapshots and tracking those damage. And we want to do that with the highest temporal and spatial precision. And this is what XFEL and future XFEL design can offer. We are using technique that are X-ray spectroscopy, ultrafast diffraction imaging. Here you have an example of DNA that is initiating in terms of damage by different type of sources. It could be the X-rays, it could be the ion beam, it could be the electron beams. And then basically the transfer of this energy is breaking at another position in the DNA. And you can actually do diffraction here and record this transfer. The advantage of those techniques is that they are site selective. They are actually happening in time scale that the XFEL covered. So this is a unique opportunity to look in those time scale. And of course, there is some future developments to go towards nonlinear capability because of this high intensity that XFEL can provide. Now, the second example is in X-ray attosecond physics. The idea here is to capture the ultrafast motion of electron holes that are created in matter. And by attosecond, for those of you who don't know, this is 10 to the minus 80 seconds, so it's very, very fast. And what we are trying to do is to track the transfer of electronic excitation to another site of the matter. So the type of technology that we use or methodology is multidimensional spectroscopy, impulsive X-ray Raman scattering. Here you have an example of an excitation that is then propagating into another site here, into this molecule. And the advantage of it is that we can take the outstanding capability of XFEL to empower those type of techniques. So making use of the tunability of the XFEL that is expanding to extend the whole range of application of those techniques, we can also think about multicolor scheme with XFEL that is now possible and will be possible even more in the future. And of course, this idea of tracking the electronic transfer is a very general concept. And the application in the future will definitely be in quantum control of systems, photocatalysis, and even light harvesting and renewable energy. I wanted to show you also another example in the same direction, which is basically impulsive X-ray Raman scattering in liquid. This has been done at LCLS in 2020, and that shows you this capability to go beyond the gas phase, but also in the liquid phase for discovering this, capturing this dynamic. So finally, I would like to mention what would happen if we increase the intensity of this XFEL, and then there is a completely dream come true that is happening. We can basically study light matter or X-ray matter interaction under extreme conditions. And this is a proposal here of experiment that will take advantage of laser plasma physics, wake field. And the idea would be, so for example, this idea here would be to focus the XFEL into a bulk and generating from that attosecond electron beams. This hasn't been done, and this would be possible. There is also the possibility of creating virtual electron positron pairs and polarized vacuum and study this. And of course, the natural decay of this phenomena would be to have like a isotropic distribution of emission of these virtual electron pairs. And with high intensity, we can go even further into the relativistic capability and also exploring non-perturbative quantum electrodynamic. Okay. So those were 3 examples, but of course the list is much longer than that. We can understand, we want to understand energy transfer, of course, so new X-ray spectroscopy, as I just presented. We can also look into chromophore properties, so basically the fact that the molecule will change conformation and will have different properties. We can also look into, which would be molecular functionality application. We can also sense chirality with X-rays. We can look into doing X-ray diffraction imaging in single molecule. We just heard about it just before. And there is also a new realm of imaging technique that is open by kind of like combining what is happening in the quantum optics physics and applying it to the X-ray. So ghost imaging, quantum diffraction, for example. Of course, there is this attosecond timescale opportunity that exists with XFEL with this brilliance. And we can think about studying core dynamics. So when you remove an electron from the core and what is happening after that. And of course, there is a lot of application into light inducing extreme condition for matter. I just mentioned basically the polarized vacuum, but there are also the possibility to study action-like particles and provide a new route maybe to detection of dark matter. As Alan mentioned, there is a lot of synergy as well. We can have some synergy with plasma wake field acceleration and think about producing a new type of gamma rays line. So we start the new opportunity in physics. They are exciting because there is new fundamental physics to be discovered. We have basically impact in potential energy and net zero, dynamic of radiation damage in biomolecules, sensing chirality, new quantum control capability, and also extending basically the knowledge that we can have into extreme matter under extreme conditions. And the exciting and unique opportunity that we have here is to have a fantastic impact in the private sector. We can think about new measurement method invention. We can think about energy transfer, energy renewal protocols, new detector technology. And obviously at megahertz, we have to ask the question about the data processing as well. So with this, I hope I'm on time. My presentation is finished. And thank you for your attention.